Okay, so we were talking in the past couple videos about energy going into particles or coming out of particles, depending on what we're dealing with, an exothermic or an endothermic reaction. In this video, I'm going to talk about just what sort of symbols we use to express the quantitative amounts of energy. So first of all, I'm going to use, I'm going to erase it here just a second. There we go. I'm going to use the letter E to represent the energy. And this is going to be like the total amount of energy. That is going to depend on two basic things. First of all, a number of moles, N, and the actual energy change of the individual atoms or particles, delta H. Delta H is defined for 1 mole. So this is really the energy per mole. And note here with energy is always relative to some fixed reference point. Again, using our simple example of the hill, if we want to state the energy a ball has at the top of the hill, we kind of need to know what height 0 is, or where energy 0 is. So if this hill is 5 meters high, we've measured that height relative to the ground level. So we're calling the ground level height 0. And so really what we're doing is we're saying energy is 0 at this fixed reference point. So here we can say energy is equal to whatever it is based on the fact that it is that much more than 0. With chemicals, we actually don't have as good of a fixed reference point to work with. What we use instead is the energy associated with the elements in their, the atoms that make it up in their elemental form. So we would say the energy of O2 is 0. Even though there's a bond formed there, and that doesn't mean that there's really no energy at all, we need to call somewhere 0. So carbon, as it would exist, would have a 0 energy, any element, right? So energy is equal to 0 for the elemental forms. This works as a pretty good reference point, because then when they form bonds, we can say they either are more stable or less stable than they were as elements, and when that happens, then we can define all of our delta H's relative to the energy the atoms had when they were an element. So then we can define delta H through these energy of formation equations. Let's say we're dealing with water, for example. So we want to make water. We want to make water out of its elements, H2 and O2. We need to balance these formation equations, but unlike normal equations where we can't have fractions in this balanced chemical equation, because we're simply trying to find out the energy for one mole of water molecules, I can use fractional coefficients to balance this. So I can say that this energy of equation is H2 plus 1/2 O2 to form that H2O. I don't have to go 2, 1, 2 like I would in a normal situation, because again, I want to make sure this coefficient works out to 1. If this happened in real life, and it was 1 mole of the reaction happening, then produced in this reaction as well, because this bond formation would be exothermic, this is more stable. So it's going from a high energy state to a low energy state. The energy that would be available to the environment is 285 kilojoules per mole. I'm getting this value out of a chart. I don't know this or anything like that. I just happen to have a chart with me here. Anyway, so what that would mean then is the environment energy would receive that 285 kilojoules per mole. Because delta H is expressed from the point of view of the atoms, they're going from here to here, so this is a decrease, this is a negative, right? Let's say this was 0. How far down did they go? They went down negative 285 kilojoules per mole. Then delta H here is negative 285 kilojoules per mole. So this is a negative heat associated with this reaction, and a negative heat or a negative energy change associated with the reactants. If that's true, that energy is available to the environment, and it means that this is an exothermic reaction. So a negative delta H value is associated with an exothermic reaction. We went from a relatively unstable state to a stabler state. The elements in this case are not as stable as the final product. I feel like we should just take half a second and look at the opposite. Let's say, for example, O2 is forming into ozone, O3. This is not actually a favorable reaction. O2 is actually more stable than O3. That's why this reaction only happens in the upper atmosphere, where there's all kinds of ionizing radiation that's available as extra energy to make this reaction happen. This would be balanced like this, so that we can make sure we're getting 1 mole of our O3 being produced. And we wouldn't get energy over here because it was more stable in the first place, so it's not releasing energy, it is instead absorbing energy. I can probably look up here what ozone is. Positive 142.7. So it's actually 142.7 kilojoules per mole. So that means if 1 mole of this reaction happened, it would need 142 kilojoules to be put into the reactants. So we would start from a low value and go up to a higher value, in this case 142.7. Here you'll notice, as with the last example, I've defined 0 as my naturally occurring element. So where does that energy come from? Well, that energy comes from the environment. So this is an endothermic reaction. Energy is coming from the environment, going into the products, and this reaction is actually going to get colder. Here, because the elements themselves are going to a higher state of energy, our delta H is a positive 142.7. Energy goes in. And as we said, then positive delta H values will be associated with endothermic reactions. So the total amount of energy associated with this reaction would take those delta H values that we just discussed and then multiply by the number of moles to account for the amount of substance that's actually gone through the reaction. And this would be the energy change associated. Remember, these delta H's were from the perspective of the reactants. So this is the energy change associated with the reactants. So energy total depends on how much we have plus the actual change associated. We do both in terms of the mole, so how many moles we have, and then the energy change per mole. We need a reference point. The reference point we're going to use over and over again is going to be the elemental forms. That's the standard for chemical reactions. So even though O2 has a bond formed in it, it might not seem like the most obvious place to set 0 energy, but when we consider what we're mainly interested in is O2 coming together with other things to form other stuff, then O2 is usually our starting point, so that does make a good reference or 0 energy point. We just have to pick that. So that's what everybody's picked. So when we consider the energy associated with an individual molecule, we can call that the energy of formation of that molecule. So, for example, water being formed out of H2 and a half of an O2 to make one H2O molecule, we figure out that 285 kilojoules per mole are released when that happens. We could do that experimentally. That's associated with those water molecules, or the hydrogen and oxygen going to a more stable state or a lower energy associated with water. And so if they decrease in energy, their delta H value would be negative 285 kilojoules per mole. And this is an exothermic reaction because that 285 is available to the environment. Alternatively, if we consider a reaction that does happen, but that is bad from an energy perspective, the formation of ozone, O2 was more stable than it, so this is actually going to a higher energy. This led to our delta H being positive in an endothermic situation where energy was required from the environment to make this reaction happen. This total energy then is going to be this delta H, positive or negative, depending on whether it's endo or exothermic, times the actual number of moles.